Jai Hind students, welcome to my YouTube channel. Students, kindness and caring are the sweet nurturing soil from which the seeds of love spring forth. So what it means is that although acquiring knowledge, obtaining marks, these are quite important for being successful, but this is not the end of it. Actually, you need to have that caring attitude. You have to have that loving attitude. It is only then that a person can become a real successful person. Clear? So these are very, very important ingredients in one's life. Love, care, kindness. So please try to develop these qualities. Right? Okay, students. In this session, we are going to discuss a very, very important topic of moving coil galvanometer. It is also known as fixed magnet moving coil type galvanometer. As the term suggests, here the coil will move, but the magnet will remain fixed. Right? So, let's start with the introduction then. Moving coil galvanometer, students, it's a very, very sensitive device and it can be used to detect, measure, as well as detect the direction of the flow of current in a circuit with the help of angular deflection. It was first designed by Kelvin. And later on it was modified by T. Arsenault. And students, with suitable modifications, a moving coil galvanometer can be converted into an ammeter as well as it can be converted into a voltmeter. That we'll discuss in the next lecture, right? That is also a very, very important topic. So, galvanometer, which we are discussing over here, is a fixed magnet moving coil type galvanometer. Here the coil will get deflected about its axis while the magnet will remain stationary, it will remain fixed. And as I told you, it's a very, very sensitive device which can be used to detect, measure. It can also be used to determine the direction of the flow of current through a circuit. Right? Principle. We already are aware, students, whenever a current carrying coil is placed under the influence of magnetic field, then what happens is it experiences a torque. Torque a body will experience only when it is under the influence of two equal and opposite forces, isn't it? And those two forces should be equal, opposite and have different lines of action. So as a result of which what happens is the coil tends to rotate about its axis in a particular direction. So that deflection, by noting that deflection, we can detect or measure the current. Right? I will explain with the help of a simple analogy. Suppose, students, in the previous lecture I have discussed this case in detail. Right? Let me recap that. This is a rectangular frame over which number of turns of copper wire is wound. This is A, B, C, D. And suppose the current is flowing in the anti-clockwise direction. And it is under the influence of uniform magnetic field, directed from left to right. Now we have discussed, students, this arm AD, it experiences a force F1 is equal to BIB cos theta along the axis in the upward direction. This arm BC, it will experience a force BIB cos theta along the axis in the downward direction. So F1, F2 being equal in magnitude, opposite directed and having the same line of action will tend to get cancelled out. They will nullify the effect of each other. While on the other hand, students, this arm AB, it tends to experience a force in the outward direction, BIL. While this arm CD, it tends to experience a force in the inward direction, again BIL. Now this force F4 and F3, these two are again of equal magnitude, each being equal to BIL. L is the length and B is the breadth and capital B is the strength of the magnetic field. So these two forces, F3 and F4, being equal in magnitude, opposite directed, but most importantly having different lines of action They are acting anti-parallel. It is acting along this line, and this force will act along this line. So these two forces will constitute a torque, and as a result of which what happens is it will get deflected. This coil will be suspended with the help of suspension wire, and the other will be connected to a hairspring. So under the influence of this deflecting torque, this coil will get deflected like this. Now what happens is, as the coil gets deflected, the suspension wire will get twisted, and due to the spring action, a restoring torque is developed, which tend to bring the coil back to its mean position. But students, due to the inertia of motion, this coil overshoots its mean position and go to the other extreme. And then again, restoring torque is developed. It tends to bring the coil back to its mean position. So again, due to inertia of motion, it will overshoot its position and go to the other extreme. So as a result, it can give deflection like this. Depending on the direction of the current, it can give deflection either towards anti-clockwise direction or in the clockwise direction. Clear, students? And a pointer is connected to the coil. So as the coil gets deflected, this pointer will also give some angular deflection. So by noting down the angular deflection given by the pointer, the current flowing through the coil can be measured. So this is the use of moving coil galvanometer. So before we proceed with its construction and working, I would like you to watch this short clipping, right? A moving coil galvanometer is a sensitive device which is used to detect small current flowing in an electric circuit. It has two concave poles of a strong permanent magnet. It consists of a rectangular frame over which number of turns of conducting wire is wound, and one end of the coil is suspended from the torsion head with a phosphor bronze wire. The other end of the coil is attached to a hairspring. As the coil rotates under the effect of the torque, the suspension wire gets twisted and a restoring torque is developed in the suspension wire. So that's the use of this hairspring. The coil will rotate till the deflecting torque acting on the coil due to the flow of current is balanced by the restoring torque developed in the suspension wire due to twisting. It also consists of a soft iron core. It increases the effect of the magnetic field and also provides a radial magnetic field. A pointer is connected to the coil, which is used to give an angular deflection. The two ends of the coil are connected to the two terminals of a galvanometer. With suitable modifications, a galvanometer may be converted into an ammeter or a voltmeter. Now, the working principle of the galvanometer is based on the fact that whenever a current carrying coil is placed in a magnetic field, then it experiences a torque. So let us consider this to be a rectangular coil, and it is placed under the influence of uniform magnetic field directed from north to south, that is from left to right. Suppose the current in the coil be flowing in the clockwise direction, that is from A, B, C, D, as shown by the green arrows. As the current is made to pass through this rectangular coil under the influence of magnetic field, it experiences a torque. The arm AB, it experiences a magnetic force directed inwards, while the other arm CD, it experiences a magnetic force in the outward direction. These two forces, being equal in magnitude, opposite directed, and having different lines of action, will constitute a torque. Okay students, I hope you have enjoyed watching this short clipping. Now I will try to recap the entire construction of the moving coil galvanometer. So students, this is the moving coil galvanometer, right? Here you can notice this is a rectangular frame over which number of turns of conducting wire are wound, right? This is A, B, C, D. It's a rectangular frame over which number of turns of copper wire are wound. And this rectangular frame is suspended between the torsion head and the hairspring. It is connected to the torsion head with the help of a suspension wire, which is made up of phosphor bronze strip, right? And in between a mirror is placed. Actually, this mirror, with the help of lamp and scale arrangement, can be used to measure the angular deflection, isn't it? And this is the hairspring. And students, this frame is suspended between these two concave poles of a strong magnet. And this entire arrangement is enclosed in a non-magnetic casing. Casing means covering, so as to avoid any sort of air disturbance, right? These are, students, the leveling screws. These are used so as to place the arrangement on a perfectly horizontally, so that the coil can oscillate freely without touching the poles of the magnet. And remember, students, this rectangular frame, it consists of a central cylindrical soft iron core, and that is stationary. The frame, that is the rectangular coil, it will get deflected, isn't it? But that cylindrical soft iron core, that will remain stationary. And T1, T2 are the two terminals through which at one terminal current will enter, through the other terminal current will leave, right? Now let me level this diagram for you. This is, as I told you, this is the non-magnetic casing. It is a non-magnetic casing. Casing means covering. It's a non-magnetic casing. This is the torsion head. This is torsion head. This is a mirror. As I told you, it is suspended along with the phosphor bronze strip, and this mirror along with lamp and scale arrangement is used to measure the angular deflection. This is phosphor bronze strip. Phosphor bronze strip. It's a suspension wire, and if it is in the form of quartz fiber, then it would be much better. So phosphor bronze or quartz fiber, right? And these are the two terminals. T1, T2 are the terminals. These are north and south. These are the concave poles. Look, these are the concave poles. We'll discuss it while we discuss the working. The concave poles of a magnet, it provides radial magnetic field. Yes, radial magnetic field. So what's the importance of radial magnetic field? That we'll discuss in detail. So these are the concave poles. And this is a rectangular frame. It is a rectangular frame over which number of turns of copper wire is wound, right? And this is hairspring. This is, as I've told you, it is hairspring. Basically what happens is, as the coil gets deflected when the current is made to pass through the coil, then what happens? It provides a restoring torque, right? So that again we will discuss. These are the leveling screws. This is a leveling screw. And this is a soft iron core. It is a soft iron cylindrical core. Soft iron cylindrical core. Soft iron, students, it's a ferromagnetic material. So all the field lines tend to pass through the ferromagnetic material, and it also increases the effect of the magnetic field. This also we'll discuss in detail, right? And these are the terminals that I have told you, and these are the number of turns of copper wire, or number of turns of any conducting wire, right? So this is regarding the construction part. Again I repeat, students. Moving coil galvanometer, it consists of a rectangular frame over which number of turns of copper wire is wound, right? It is suspended between the two concave poles of a strong magnet. One end of the frame is connected to the torsion head with the help of suspension wire, made up of phosphobronze or quartz. In between a mirror is placed. Mirror with the help of lamp and scale arrangement can be used to measure the angular deflection, right? The other end of the frame is connected to the hairspring. It provides the restoring torque. And this frame consists of soft iron cylindrical core that is stationary, right? And it is used so as to increase the effect of the magnetic field. And soft iron, being a ferromagnetic material, all the magnetic field lines tends to pass through the soft iron core. So it provides a radial magnetic field. We'll discuss it. The concave poles along with that soft iron core will help in producing radial magnetic field. These are the leveling screws which are used to place this arrangement perfectly horizontally so that the coil may oscillate freely without touching the poles of the magnet. And students, in order to avoid any sort of air disturbance, the entire arrangement is enclosed in a non-magnetic casing, and T1, T2 are the terminals. Suppose the current enters from the terminal T1, then what happens is this current, this is how the circuit will get completed, right? The current will flow in the direction ABCD, like this. ABCD. This is how the current flows, and then it will come out of terminal T2. This is terminal T2. So T1, T2 are the terminals across which at one terminal the current will enter, while at the other terminal the current will leave. This is how the circuit gets completed, right? Basically, current needs to be passed through this rectangular coil ABCD, right? And we have considered the current to be passing through the rectangular coil in the anti-clockwise direction. So that's the construction part. I hope it's pretty clear, students. There shouldn't be any sort of doubt regarding this, right? And normally a pointer is connected with the coil. So as the coil gets deflected, the pointer also shows deflection, and we can make use of a graduated scale so as to read the current. So actually, what our objective is that the deflection produced in the coil should be proportional to the current flowing through the coil. So how to achieve that, that we'll discuss in the working part, right? So let's concentrate on the working of a moving coil galvanometer. Students, we are aware that whenever we consider a current carrying coil under the influence of magnetic field, then as you are aware, it experiences a torque, isn't it? And that torque, what it results is, it results into making the coil to rotate about its axis in a particular direction. So as the rectangular coil under the influence of this deflecting torque rotates, the suspension wire, it will get twisted, and accordingly, due to the action of this hairspring, a restoring torque will get developed, which will tend to bring the coil back to its mean position. But again, due to the inertia of motion, it will overshoot its mean position and go to the other extreme. So as a result, it will keep deflecting like this, right? So at equilibrium, that deflecting torque is equal to the restoring torque. Anyway, let's first discuss about the deflecting torque. Students, concentrate on this particular diagram. This we have earlier done. This is A, this is B, this is C, this is D. Suppose the current is flowing in the anti-clockwise direction, and this is the axis, and it is under the influence of magnetic field. B, it stands for the magnetic field. Now students, we are aware that if we consider arm AD, then it experiences a force in the upward direction, and this force is given by BIB cos theta. This is length of the rectangular coil, and B is the breadth of the rectangular coil. This article has already been done in the previous session, right? If you consider arm BC, it experiences force F2, and its magnitude is same, that is BIB cos theta. Now these two forces being equal in magnitude, oppositely directed and having the same line of action will tend to cancel out the effect of each other, right? Now if you consider arm AB, then it tends to experience a force in the outward direction, and this force was found to be BIL. B is the strength of the magnetic field, I is the current, L is the length of the rectangular coil under conservation, right? This is in the outward direction. And on the arm CD, it will experience a magnetic force in the inward direction. Its magnitude is again same, BIL, and in the inward direction. So students, look, F3, F4 both are of equal magnitude. They are opposite directed, but the most important point is they are having different lines of action. So they don't nullify the effect of each other. Instead, F3 and F4 being equal in magnitude, oppositely directed and having different lines of action will constitute a torque. And under the influence of that torque, the coil will tend to rotate about its axis in the anti-clockwise direction like this. And students, this deflecting torque, we are aware, this deflecting torque, it is given by, we have proved it, it is given by N, B, I, A sin theta. This is the expression for the deflecting torque. N, it is the number of turns of the conducting wire which is moved over this rectangular frame, right? B obviously is the strength of the magnetic field. I is the magnitude of the current flowing through that particular coil. A is the area of the coil, which in this case being rectangular would be length into breadth. Theta, students, it is very, very important. Theta, I have told you, it's the angle between the magnetic moment and the magnetic field. Now always remember, magnetic moment due to a current carrying coil is always perpendicular to the plane of the coil. That is, theta may also be said to be the angle which the magnetic field makes with the normal to the plane of the coil. So, if this is the normal, then this is the angle theta. This is angle theta. This is magnetic field and this is normal N. So this is angle theta, right? So if this is the normal, so this will be the angle theta. So theta, students, always remember, it is the angle which the magnetic field makes with the normal to the plane of the coil. Or theta is the angle which the direction of the magnetic field makes with the magnetic moment of the current carrying coil. Magnetic moment is always directed perpendicular to the plane of the coil. Clear, students? There shouldn't be any sort of confusion. So, deflecting torque is given by NBIA sin theta. That's deflecting torque. This is the expression for the deflecting torque, which we have already done in the earlier session, right? Now, students, think, as this coil under the influence of this deflecting torque rotates, what will happen? Obviously, the suspension wire, it will get twisted. It will get twisted. So, as a result, what happens is a restoring torque will get developed, which will tend to bring the coil back to its mean position. So, I will elaborate with the help of this diagram. Just concentrate on this diagram. Suppose this is the suspension wire. This is the suspension wire, right? This is the magnified view of this suspension wire. Now what happens is, suppose point P is over here. Now due to its twisting, it is getting deflected in the anti-clockwise direction. Now due to its twisting, what happens is this point P will change its position, say, to point P dash. Therefore, with respect to a particular point, it will get twisted through some angle. This angle may be considered to be phi. So this is the angle of twisting. This is the angle of twisting. Again, I repeat, students, as the current is made to pass through this rectangular coil, which is under the influence of this magnetic field, what happens is it experiences a torque due to which this coil will get deflected about its axis in the anti-clockwise direction. So it is not free to oscillate, isn't it? It is suspended between the two wires. One is the suspension wire which is connected to the torsion end, the other one is connected to the hairspring. So as under the influence of this deflecting torque the coil gets deflected, then what happens? The suspension wire, this wire will get twisted. It will get twisted. So suppose phi is the twisting angle. Phi is the angle through which the wire get twisted. Now what happens is, due to the elasticity, a restoring couple, a restoring torque will get developed, which will tend to bring the coil back to its mean position, right? So suppose let C be the restoring torque. Let C be the restoring torque developed in the suspension wire per unit twist. And one thing more, students, the more the angle of twisting, the more will the restoring torque developed in it, isn't it? What I mean to say is that, suppose this is phi, twisting angle, and this is the restoring torque. This is the restoring torque, right? So, for 1 degree of twisting, the restoring torque developed is C. C is also known as the torsional constant. The C is also known as torsional constant. The C is also known as torsional constant or torsional strain. Right? Okay. Now look, C is the restoring torque developed in the suspension wire per unit twist. That is, for 1 degree angle of twisting in the suspension wire, the restoring torque developed is C. For 2 degree angle of twisting in the suspension wire, the restoring torque developed in the suspension wire would be twice C. Is it clear, students? Therefore, for 3 degree angle of twisting, it will be 3C and so on. So as I've told you, with the increase in the twisting in the suspension wire, the restoring torque will also increase accordingly or proportionately. Therefore, for phi angle of twisting, the restoring torque will be given by C phi. Therefore, students, the restoring torque for angle of twisting of phi, it will be given by C phi. So again I repeat, students, C is considered to be the restoring torque per unit twist developed in this suspension wire, right? For 1 degree twisting, the restoring torque developed in the suspension wire is C. And as you are aware, with the increase in the twisting, the restoring torque developed in the suspension wire will also increase. So for phi angle of twisting in the suspension wire, the restoring torque developed in the wire will be C into phi. C is the constant which is known as torsional strain or torsional constant. It is actually the restoring torque developed in the suspension wire per unit twist. Clear, students? Now at equilibrium, what will happen? The deflecting torque would become equal to the restoring torque, isn't it? So let's proceed further. At equilibrium, the restoring torque would be exactly equal to the deflecting torque. So what we get is, okay, right, at equilibrium, this deflecting torque would become equal to the restoring torque. Right? So, if you substitute this value over here, what do you get? N d I a sine theta, it's equal to C phi. In case we rearrange the terms, so we can write it like this: I is equal to C divided by NBA, and over here phi divided by sine theta. Right? Students, for any given galvanometer, the term which I have written inside bracket is constant for any given galvanometer. Right? So, this term is known as the galvanometer constant. So, I is equal to capital G phi divided by sine theta. Here, G is equal to C divided by NBA. This is known as galvanometer constant. It is known as galvanometer constant. For any given galvanometer, N, the strength of the magnetic field, the area of the coil, C, it depends on the nature of material of the suspension wire, that all will remain constant. So, for any given galvanometer, this term C over NBA is constant and is known as galvanometer constant. Students, what will be its dimensional formula? What is the SI unit or the dimensional formula for the galvanometer constant? Make use of your common sense. Now look, this term, this is phi, dimensionless. Sine theta, all the trigonometric functions are dimensionless. So it has got no dimensions. And for this relation to hold valid, the dimension of left hand side should be equal to the dimension of right hand side. So current, it is ampere. So G must also have SI unit of ampere. So SI unit of galvanometer constant is ampere. Right? So its dimensional formula would be A, capital letter A. So this is the expression for the current. Now look students, we need to concentrate on this particular expression. I equals to G phi divided by sine theta. G is, as I told you, for a given galvanometer, it is constant. Now, phi over sine theta. This is the deflection suffered by the coil, isn't it? We want a linear dependency between the deflection produced in the coil and the current that is being passed through the coil. So in order that the deflection produced in the coil be directly proportional to the current made to pass through the coil, we need to eliminate this term sine theta. Isn't it? Again I repeat students, in order to make use of a linear scale where we can say confidently this first deflection, so this is the current. If the deflection is made twice, the current will make twice. Or if the current is made thrice, the deflection will also increase by 3 times. If the current flowing through the coil is made 4 times, the deflection should also be 4 times. So, in order to have a linear scale between the angular deflection and the current flowing through the coil, there should be a linear dependency between I and phi. That is, I and phi should be directly proportional to each other. For that, students, this is constant. So, we need to eliminate this term sine theta. Again, I repeat, students, in order that the angular deflection produced in the coil be directly proportional to the current flowing through the coil, the term sine theta must be eliminated. Suppose sine theta term is eliminated, then what will be the expression? I would be equal to G phi. G is constant, so I would become directly proportional to phi, which means that we can make use of a linear scale so as to measure the current, which will be entirely directly dependent on the deflection produced in the coil. The more the deflection, it means that more is the current flowing through the coil, isn't it? So again I repeat, students, this is a very, very important statement, right? In order that the deflection produced in the coil be directly proportional to the current flowing through it, the term sin theta must be eliminated. Somehow we need to think of some method in which sin theta gets eliminated. And students, for that we make use of radial magnetic field. Now in the next few minutes I will be explaining how by using concave poles, that is by obtaining radial magnetic field, the term theta can be made 90 degree. So that sin 90 would become 1. So as a result, sin theta will get eliminated. So we will get direct relationship between I and phi. Right? Let's discuss that. So next is the use of concave poles. Now students, look. Theta, as I have told you, it is the angle which the normal to the plane of the coil makes with the direction of the magnetic field, right? Now, suppose this is the case. Suppose these are not concave poles, these are straight poles, north and south. This is the direction of the magnetic field. Now, if you get a top view of this coil, top view, right, then the diagram will be somewhat like this. We'll be able to see only this portion AD, right? AD. This is the magnetic field. This will be the normal or magnetic moment. This is angle theta. As the coil gets deflected, then the value of theta will always get changed, isn't it? This theta will get changed as the coil gets deflected. This is by using straight poles. Now, what will be the benefit of using concave poles? That we will discuss. So, concave poles. Students, please concentrate on this particular diagram. So, if you just imagine to view this apparatus from the top, then these being the concave poles, it will appear like this. This is the north pole and this is the south pole. And this is the soft iron core. This is the soft iron core which is in the cylindrical form. This is the soft iron core. Right? It is in the cylindrical form, in the form of a cylinder. This is the soft iron core. As I told you, students, soft iron is a ferromagnetic material. All the magnetic field lines tend to pass through this material, and also it increases the effect of the magnetic field. Okay. And AD portion. First, let me draw the field lines over here. Now, this is the field line. And over here, it will be like this. All the field lines will pass through the soft iron core. Like this. So, instead of getting straight lines like this, we will obtain the radial magnetic field. This is known as radial magnetic field. So, this is radial magnetic field. So, which property is being used over here? Soft iron is a ferromagnetic material, and we'll discuss it in detail in the next unit of magnetism. A ferromagnetic substance, it has got a large value of susceptibility. It has got a large value of relative permeability. So what happens is, in case it is placed in a region of magnetic field, then all the magnetic field lines tends to pass through it. Right? So that's the purpose of making use of soft iron core. So students, as I told you, it's a radial magnetic field, right? Now, if we view this arrangement from the top, then the diagram would be like this. And let's represent this arm AB. From the top view, only the arm AD of the rectangular coil would be visible to us, right? So, it will be somewhat like this. arm AB of the rectangular frame ABC. This is the top view. This is A and this is B. This is the top view. So students, basically observe and try to bring out the essential point where you have noticed in this diagram. In this case, what happens is, as the coil rotates like this, as it gets deflected, the angle between the magnetic moment and the magnetic field will keep on changing. Theta is a variable over here. Theta will keep on changing as the coil gets deflected. But in this case, students, look, this is the normal to the plane of the coil, which is the direction of the magnetic moment as well, and this is the magnetic field. This is the magnetic field, right? So the magnetic field lines are along the plane of the coil, and this is the magnetic moment. So what is the angle between these two over here? It is 90 degree. Not only in this position, but at any position, any orientation of the coil, the magnetic field line will be always along the plane of the coil, so that the angle between the magnetic field and the magnetic moment, or the normal to the plane of the coil, will be always 90 degree. Look, if the position or orientation of the coil get changed like this, then also the magnetic field line, as you can notice from this is the magnetic field line. This magnetic field line will be along the plane of the coil. So the angle between the magnetic field and the normal to the plane of the coil will always be 90 degree. Students, at this orientation, this is the magnetic field line which will be along the plane of the coil, isn't it? So as a result, the direction of the magnetic field and the normal to the plane of the coil will be again 90 degree. So understood the significance of using radial magnetic field? By using radial magnetic field, the angle theta, which is the angle between M vector and B vector, can be made 90 degree, and it will be constant. It won't change. So therefore, students, by using radial magnetic field, these are the radial magnetic field, the angle theta can be made 90 degree, and it will remain 90 degree for any orientation of the coil, because at any orientation of the coil, the angle which the field line makes with the normal to the plane of the coil will always remain 90 degree. So what will be the significance then? If theta is 90 degree, then sin 90 it will become 1. So sin theta gets eliminated. So as a result, if theta is equal to 90 degree, sin 90 would be equal to 1, which implies that I would be equal to G phi. Clear, students? G, as I have told you, for a given galvanometer, G is the galvanometer constant, right? So G being galvanometer constant, which is C over MdA, therefore it can be written in this manner also. I is directly proportional to phi. This was our main objective. Our main objective was to get a linear dependency between the deflection produced in the coil and the current flowing through it. So this is the relationship which we would have expected, right? And this is obtained only by using concave poles of a strong magnet. Clear, students? So now, by using a linear scale, by noting down the deflection produced in the coil, the current which is flowing through the coil can be also measured, isn't it? So students, again I repeat, this is a very important diagram, right? Soft iron, remember, it's a ferromagnetic material. It increases the effect of the magnetic field. What happens is, when a ferromagnetic material is kept in the region of magnetic field, then all the magnetic field lines in the region tend to pass through that ferromagnetic material. So that is what it is happening over here. In the absence of soft iron core, it will be straight for straight poles. But in the presence of soft iron core, all the field lines will tend to pass through the soft iron core, so that the magnetic field lines becomes radial. And under the influence of radial magnetic field, the plane of the coil always is along the direction of the magnetic field, so that the angle which the magnetic field makes with the normal to the plane of the coil, or the angle which the magnetic field makes with the magnetic moment, always for any orientation of the coil remains 90 degree. So as a result, sin 90 will become 1, so it gets eliminated. So we get a linear dependency or direct proportionality, direct relationship between phi and I. So now a linear scale can be easily used so as to measure the current by noting down the deflection produced in the coil. So this is the principle. So basically a pointer is connected to the coil, and with the deflection in the coil, the pointer, if the graduated scale is used, then it can be used to measure or detect the current flowing in the circuit. Right, students? So now, since we have done intro, principle, construction, working, we have also done importance of radial magnetic field. It's a very, very important concept. Now the last topic is left, which is the sensitivity of a galvanometer. Now students, look, a galvanometer is said to be sensitive if it produces large deflection even when small current is made to pass through it. So that is when the galvanometer is said to be sensitive. So we will discuss its current sensitivity as well as its voltage sensitivity. So again I repeat, a galvanometer is said to be sensitive if it is able to produce large deflection even when small current is made to pass through it. Right? So there are two types of sensitivity which we are going to discuss. First is the current sensitivity. Current sensitivity. We can represent it by CS, current sensitivity. It is actually the deflection produced in the galvanometer per unit current which is passing through the coil. So this is known as current sensitivity. Phi is the deflection produced in the coil, I is the current flowing through the coil, right? So from here students, phi by I, it will be equal to reciprocal of the galvanometer constant, and this in turn would be equal to NBA divided by K. This is the current sensitivity, right? So current sensitivity of a moving coil galvanometer is defined as the deflection produced in the coil when unit current is made to pass through it. So mathematically it is phi by I. So from here, phi by I would be reciprocal of G. G is the galvanometer constant. G, as we have discussed earlier, it is the galvanometer constant. It is equal to K over NBA. In fact, C over NBA. We have represented the torsional constant with C, isn't it? So it is C divided by NBA. So here we get NBA divided by C. C is the torsional constant. Right, students? Now, voltage sensitivity. It can be represented by Vs. As we have defined current sensitivity, in the similar fashion, the voltage sensitivity may also be defined. Voltage sensitivity may be defined as the deflection produced in the coil when the terminals are maintained at unit potential difference. So divided by V. So the deflection produced in the coil divided by the potential difference applied across the ends of the coil. Right? So it would be phi divided by IR. V equals to IR. R is the resistance offered by the coil. Right? R is the resistance offered by the coil. So what we get is phi by I is current sensitivity. So it is equal to current sensitivity divided by R. Or voltage sensitivity is equal to current sensitivity, that is NBA divided by C and this R. So this is the expression for the voltage sensitivity. Again I repeat students, the deflection produced in the coil per unit current passing through the coil, that is known as current sensitivity. And the voltage sensitivity of a moving coil galvanometer is the deflection produced in the coil when unit potential difference is applied across its terminals. Right? So this is the expression for current sensitivity and voltage sensitivity. Now let's discuss how to increase the sensitivity of a galvanometer. Right? Now how to increase the current sensitivity? You can increase the number of turns, you can increase the strength of the magnetic field. Increase in the area of the coil is not at all preferable. Why? Because it will make it bulky, right? Which is not at all preferable. So, increase in the area of the coil is not at all preferable. And reducing the value of C. So, these are the options. So, the current sensitivity of a galvanometer can be increased by increasing the number of turns, by increasing the strength of the magnetic field. And how the strength of the magnetic field can be increased? In case we are using electromagnet, then the current, the magnitude of the current can be increased, or we can make use of a strong concave poles of a strong permanent magnet, right? And students, as I told you, increasing A is not at all preferable. It will make the apparatus bulky, right? C is torsional constant or torsional strain. It should be less. So we need to choose that material of a suspension wire for which the value of C is less. And students, this is the reason why we make use of phosphor bronze, because for phosphor bronze the value of C is smaller, and for quartz the value of C is still smaller. So as a quartz, if you use suspension wire, that is more preferable, but that is obviously more costly, right? So students, what are the three options by which the current sensitivity of a galvanometer can be increased? First is by increasing the number of turns, by increasing the strength of the magnetic field, and by choosing the material of a suspension wire for which the value of C is small. For that we make use of phosphor bronze or quartz. For both phosphor bronze and quartz, the value of C, which is the torsional strain, is very less. C actually is the restoring torque developed in the suspension wire per unit twist, right? Now let's see how to increase the voltage sensitivity of a galvanometer. Here we can increase strength of the magnetic field, we can decrease the value of C as we have discussed in the case of current sensitivity as well. But a very important point to be noted is that students, increasing N won't affect, won't change, won't increase the voltage sensitivity of the galvanometer. Why? Because if we make the number of turns as twice, then by increasing the number of turns, the length will also increase, and resistance, other factors remaining constant, it is directly proportional to length. So new resistance will also become twice. So if you substitute over 2N, here 2R, 2 will get cancelled, so the voltage sensitivity will remain same. So students, please keep this in mind. Increasing the value of the number of turns won't affect the voltage sensitivity, because with the increase in the number of turns, the resistance offered by the coil will also increase accordingly. So being the ratio of N by R, that will remain constant. So voltage sensitivity will remain constant. So in order to increase the voltage sensitivity of a galvanometer, B should be made as large as possible. C should be very, very small. For that I have made it very clear. We make use of phosphor bronze or quartz. And R should be less. And that's why we make use of some good conducting wire, right? Which offers low resistance. So students, key point. By increasing N number of turns, the current sensitivity of the galvanometer can be increased, but the voltage sensitivity will remain constant. Clear, students? So, this is the end of this particular topic, which is very, very important one. In fact, this question can come in the 5 marks category, right? So, it's very, very important. Do each and every concept, and you should be thoroughly aware of every concept used in this article. Right, students? So, do practice all these diagrams, and this was very, very important. why we make use of concave poles, what's the importance of radial magnetic field. Clear? So I hope you have enjoyed watching this session, and do practice this article, and do join me in my next lecture. Next lecture will be also the extension of this topic only. As I've told you, with suitable modifications, a galvanometer can be converted into an ammeter, as well as it can be converted into a voltmeter. So do join me in my next lecture then, so as to understand further topics, right? Till then, bye bye, and do take very good care of yourself. Stay blessed.